Today we're going to talk about the most important skill any self-respecting heating engineer should master: heat loss calculations. And joining me is Steph from Spruce, who's an engineer and an expert in heating system design.
I'll explain the theory between heat loss and what tools and methods you should use to get a really accurate result. We'll also discuss which aspects are outdated and lead to mistakes in heat loss calculations.
By the end of this video, we'll also show you how to verify your own results and build a feedback loop that will allow you to get an accurate and reliable results every single time. Tell us about your experience in the heating industry.
Yeah, so I learnt the nuts and bolts of heat loss and heat pump system design in Canada. I worked for a ground source heat pump company out there. I actually did a mechanical engineering degree, so had the theory kind of down, but only really dug into heat loss when I started that job. Sat down with the Canadian Standard on my first day, wrote out all the equations and really got my head around it. When I moved home, I worked for a retrofit startup, so learned a bunch more about the fabric and ventilation side of heat loss. And then building heat loss tools at Spruce, I've got pretty into the weeds of all of the UK standards.
So what is heat loss actually?
Yeah, so it is really exactly what it says on the tin. It's how quickly a building loses heat. But maybe before we dig into the specifics, it's really helpful to understand the difference between power and energy. So energy is the amount of heat we have. Power is how quickly that heat is moving. I find it really helpful to use a water analogy here. So energy is like volume, right? I can have a large volume of water. It is an amount, it's not going anywhere. And then I can have a flow rate. So 5 liters a minute, 50 liters a minute. That is how quickly that water is moving. And power is like that. It's that speed of heat transfer. Those things have different units. So power has units of kilowatts. That's how quick it's moving. Energy has units of kilowatt hours. And that's because energy is power times time. So if I'm losing heat at 5 kilowatts for an hour, then I've lost 5 kilowatt hours of heat.
So a bit like an electric van that might have 100 kilowatt hour battery. I wish there were vans like that. And a 100 kilowatt motor. So motor has a power of 100 kilowatts. So in theory, if you go flat out, you will deplete the battery in an hour, right?
Right, exactly. But if you had that same 100 kilowatt hour battery and you were only putting out 50 kilowatts, you're driving a bit slower, then you're going to have 2 hours of use out of that battery.
Going back to heat loss. If the building uses energy over 24 hours, is the heat loss that energy used over those 24 hours at the design temperature, or is it something else?
When we're talking about heat loss, we're talking about power.
Okay.
So how much heat is that building losing at a certain moment? And that's important to understand because how quickly my building is losing heat is exactly how quickly I need to provide heat from my heating source, be that boiler or heat pump, to keep that temperature steady in the house. If we go back to the water analogy, if I've got a bucket and I want to keep it the level of water in that bucket even, then if I'm putting in water at 5 liters a minute and losing it at 5 liters a minute, that bucket's going to stay level. Same thing in a house. I'm losing heat at 5 kilowatts. I need to provide heat at 5 kilowatts to keep that temperature in the house steady.
So that bucket analogy, we know that the driving force for the water moving is gravity. What's the driving force for heat escaping buildings?
Good question. So temperature difference is the driving force behind heat loss. So heat moves from hot to cold, just in the same way that water moves from high to low. And like with water, you need a pump to take heat from a low level to a high level. With heat, you need a heat pump to move heat from cold to hot. So that temperature difference really drives the way in which heat flows. And in the industry, we refer to temperature difference as delta T. So delta like difference and T temperature. And heat loss, so the speed at which the heat is moving, is linear with delta T, which is just a fancy way of saying if the delta T doubles, the speed of heat loss doubles.
With our bucket analogy, I can plug the hole and the water doesn't flow anymore. It's completely stopped. Can we do that with heat loss?
No. If there is a delta T across the surface, you are also always going to get some heat loss. You can slow it down a bunch. It can be fast or slow, but you're always going to get some heat transfer.
Is the heat loss a fixed number? Because we talk about a property having 8 or 10 kilowatt heat loss. We have a changing temperature outside, right? How does that work?
Yeah, exactly. So although we talk of heat loss as if it's one number for one building, actually how quickly the building is losing heat is always changing depending on the temperature inside and the temperature outside. So, if it's 10 degrees outside, 20 degrees inside versus it being 20 degrees inside, 0 degrees outside, we're going to have double the delta T, double the rate of heat loss. So when we talk about a single number for a building, what we're actually talking about is at my design outdoor temperature, what is the heat loss of the building? It's not like a fixed value that building is always losing heat at.
What is the design outdoor temperature?
The design outdoor temperature is the worst case outdoor temperature for which you're designing your heating system.
And to that temperature, we're going to be sizing our heat pumps or boilers or radiators, right?
Exactly.
Okay, so if you've got the same size houses and same design temperature, same delta T, do they have the same heat loss?
Absolutely not.
Oh.
So maybe kind of to understand that, right? Buildings lose heat in two ways. So either through the fabric, so conduction heat loss through the fabric. So that means heat loss through the windows, walls, floor, roof. And then also infiltration or ventilation heat loss, which is heat loss from the air literally escaping, through little gaps in the fabric. So hot air leaks out, cold air leaks in, and that's our ventilation or infiltration heat loss.
What controls the rate of how quickly we are losing heat through a given material?
So with fabric heat loss, there's a few important factors. One is how big is the surface area of the element that's losing heat? And then another is how conductive it is. So if I've got heat going through this window, for example, if this window is literally twice the size, then it will lose heat twice as fast. And then the other thing is the conductivity of that window. So if it's very conductive, it loses heat really quickly. If it's very insulating, it loses heat very slowly. So I might have a big window which is single glazed, so super conductive. It's going to be losing heat very, very quickly. Or I might have a little area in my loft that is very well insulated. It's got 400 millimeters of rock wool in, and that's going to be losing heat really slowly. In terms of the variables we're talking about here, this is the surface area in meters squared. And then that conductivity, we use the term U value to describe that conductivity. We measure that in watts per meter squared Kelvin. And we'll go into what those units mean in a minute. And then the third thing, obviously, that we've been talking about before is our delta T in Kelvin. So how hot is it on this side? How hot is it on that side? What is the difference between those temperatures? That's that driving force behind the heat loss. So this U value, watts per meter squared Kelvin, this is literally how fast does that power in watts go through that surface per unit area and per temperature difference.
So if you've got 1 square meter of that window and U value is 1 and the temperature difference is 1 as well, you will lose 1 watt?
You've got it.
Oh, brilliant. Let's give it a go. Let's try to calculate heat loss of this very room. Let me try to think about it. So it's a rectangular room, 5.5 meters this wall behind us, 7.2 meters this wall, laser eyes, I can tell. And 3 of those are external.
Right.
That wall there is internal, heated to the same temperature. Can I ignore that wall in my calculations?
Yeah, exactly. There's no DT across that wall.
No DT.
There's no heat loss.
5.5 times 2 is 11 plus 7.2. So you get 18.2 meters linear wall and 2.5 meters height of the room.
Yeah.
So my area of all the walls is 45.5 square meters.
Right.
But I also have those windows here, and those windows are 3 by 2 meters and 2 by 2 meters. So we've got 6 and 4, all nice numbers. So we've got 10 square meters of windows and 35.5 meters of wall area.
Right, exactly, because you've taken your windows out of your wall area.
It's an office, 21 degrees inside.
Nice.
What's the design temperature here? -3, -2. How do I know that?
Yeah, good question. So you would look that up in the SIBSI design guide for the nearest location. You'd correct it for altitude. If this was a funny altitude, this office is probably not at a very funny altitude. I actually haven't checked it, but let's go with -2. Keeps our maths.
So -2, 21. We've got a DT 23. Those are high quality double glazed windows. What U value are those? How do we know that?
So you would look those up either, you could get manufacturer's data, but normally you would look them up either from, again, the SIBSI design guide, or if you know the new build spec, what the regs were at the time, then you can use the regs at the time.
What do we say those are?
1.8.
Yeah, that's what I thought. So windows, then we've got 23, that's what RDT, times 1.8 times 10, right? So let's see what it gets us to. 23 times 1.8 times 10, 414 watts.
Sounds reasonable to me.
Okay, write it down. And then we've got walls, which is 35.5, and those are cavity insulated walls. We know that because the owner of the office told us he did insulate them. U value of 0.45, right?
0.45 is a reasonable.
0.45 is what we would find in tables for this kind of a material. And we have to also multiply it by dt.
Yeah.
All right, let's do that exercise again. 35.5 times 0.45 times 23. It's 367.42. Have I made a mistake?
I think those numbers look fine. There's some pieces that we're missing, but
Oh, right, because the wall U value is, the wall is 4 times more insulating than the windows.
Exactly.
0.45 and 1.8. So we're losing more heat through the windows than we are through the walls, although the surface area of the walls is much bigger.
Exactly.
So that makes sense. Right, ceiling. Are we losing any heat through the ceiling?
Let's assume that they're heating upstairs to 21.2.
So
then we're not losing it.
Then we would ignore the ceiling in here. If it was a roof, then we would calculate it in that similar manner.
It would be losing heat to the design outdoor temperature.
So the very last thing left here is the floor. We don't have air on the other side of the floor.
We don't.
We must have a different DT. How do we know what DT we have, and how do we know what the U value of the floor is?
Yeah, so with floor heat loss, there's actually kind of 2 cases we have. If it's a suspended floor, then we do have air on the other side. We would use the design outdoor temperature. If it's a solid floor, then we would use the average temperature in the area, which is sort of typically the ground temperature. It's probably around 11 for this location. So
I'll use 11 for here. So yeah, it is 396 watts.
You've assumed that your U value of the floor is 1.
Well, I don't have it. If it's 1, yeah, exactly.
If the floor value, yes.
Which actually by coincidence, it's an uninsulated floor.
Yeah, that might be reasonable.
Is U value between 0.7 and 1.5?
Depends a bit on the geometry of the floor. So how much exposed perimeter and area it's got, but typically around 1.
Around 1. So my total heat loss of this room is 414 plus 367.42 plus 396. It's 1177.42. So 1.2 kilowatts.
You've missed the ventilation heat loss, which
yes,
in loads of cases can be 50%, even more of the heat loss. So super important factor.
How do we calculate those?
If I go back to my pen and paper here, I've got a house. I'm going to draw it as a box. I'm no artist. It's got a certain volume and it's leaking a bunch of air out, maybe in the interfloors, around the windows, in and out. So this box, it has a volume, V, let's say, in meters cubed. This movement of air, we use air changes per hour to describe that. So how many times does all of the air in this building change in an hour? So let's say maybe once an hour, something like that. That's our ACH, air changes per hour. And then again, obviously, our delta T, the temperature difference between inside and out. So to calculate the ventilation heat loss, so our power through that ventilation, we do 1/3 times that volume times the ACH times the delta T. And that gives you your ventilation heat loss.
Why the 1/3? Where does that come from?
this is one of my favorite things about heat loss. It seems like arbitrary, but actually it's just super cool way that the physics works out. So the specific heat of air, which is like how much heat air contains, is 1,200 joules per meters cubed per Kelvin. When you convert from hours to seconds, you get 3,600. So 1,200 over 3,600, a third.
It's 1/3. If we are in this particular room and we've got 39.6 square meters floor area multiplied by the height of this room, 2.5, that's actually 99 cubic meters. So if you've got 99 cubic meters in this room and the air changes once per hour,
yeah,
I have to multiply that by a delta T of 23, right here?
Yeah.
You said 21 to minus
2.
2.
Yeah.
So I multiply it by 23, I get 2277, and I just divide it by 3.
Exactly.
And divided by 3, 759 watts.
Yeah.
So I've got 1.9 kilowatt heat loss for this room. Is that accurate?
Yeah, I think we've captured everything we need to about this room.
Great, so I've got this room done. I'm only left with about 8 more. That's gonna take me forever.
It will indeed, and that's why there's another way.
Is there?
Let me show you how I would do this.
While Steph is doing her calculations, it's worth pointing out that we are in the offices of Vito Energy in Surrey. And Vito Energy is the company where I started my renewables journey. Installing heat pumps or learning how to install heat pumps is hard enough without having to deal with tons of MCS paperwork and compliance. And that's where Vito Energy comes in. If you are installing heat pumps already, or maybe are thinking about going into renewables, Vito Energy, they do run an MCS umbrella, and I always found it first class. They have a tiered system, and they will help you depending on how much help you need with your installations. So they could supply you the kit and take care of MCS paperwork, or they could do the full design for you, including heat loss calculations. So be sure to check the links to Vito Energy below in the description to this video. How are we getting on with your calculations, Steph?
Yeah, we're already done, and it's the same result you got, 1.9 kilowatts.
Wow, that was quick. That was like 20 seconds.
Yeah, I guess that's why we built Spruce, right? It's super important for engineers to understand the principles that we've been discussing here, the why behind the heat loss calculations, but you shouldn't be going around a house faffing around trying to calculate the areas. You know, mental maths, like, sure, fun time, but you're answering a homeowner's questions, you're trying to record all the windows properly, look up the U values, do all that maths, like, that shouldn't be part of the job. And so Spruce automates all of that for you. We look up the U values so all the materials are right before you get there. You just draw those rooms, we do all the calculations, and you get your heat loss. Because it's floor plan based, we can work out the room next door. We know it's at a different temperature, get that temperature transfer across those internal walls, right? So it's just really about making it super simple. Works on your phone, works on your iPad, works offline, so can sync between different devices. You go out to a property with shitty internet, it still works for you. Just tries to make that heat loss really simple for you, really. And then kind of beyond that, it also helps with all the paperwork side of the job. You can put proposals together. Just trying to make it a seamless experience.
So we've got our results. They're pretty close, which is great. But how close are they to the actual heat loss of the property? How do we know this is not just an educated guess?
Yeah, so the fact that our numbers are the same just means we both did the right maths with the right inputs. But what the inputs are, that's the real question when it comes to accurate heat loss. If you put in garbage numbers and do the maths right, you aren't going to get the heat loss right. There's a bunch of things that people get wrong in terms of those inputs, but air changes is probably the biggest one. Most people use the SIBSI values. It very explicitly states in the SIBSI design guide that they're a worst case scenario. And so people are using these very high air change values, which typically mean that they're getting heat losses way higher than real measured values.
Is there any way we could actually verify the heat loss calculations versus what's on site, what the actual demand is?
You can indeed. So the guys at Open Energy Monitor, they have kit that you can use to measure the performance of your heat pump installation. So it measures how much electricity the unit's using, how much heat the unit is outputting, and then also the indoor temperature, and then it's got an outdoor temperature weather feed. And they're pretty smart guys. They've put together this tool that lets you actually look at all that data and understand how that building is losing heat at different DTs. So I've actually got it up here for this office. They've got Open Energy Monitor on this office. And what you see is that this follows the theory really, really well. So what's plotted here is output of the heat pump against our delta T. And you get this very clear diagonal line. So bigger the delta T, bigger the heat pump output, therefore the heat loss of the property. And what you can use this to do is to say, like, actually, okay, at my design delta T, let's say it's 23 here, what is the average heat pump output extrapolated out? It's about 5.5 here for this whole building. So if we'd have done the whole property, it would have been really interesting to see with the inputs we used, did it match that? Or like, how would we have to tweak our inputs to match that? And then, you know, next time I'm doing a heat loss, I can learn from that experience, get the inputs right, and get closer to that real value.
That's exactly what we have been doing in our company. We've installed over 20 Open Energy Monitor kits, and we've been comparing them to our heat loss calculations. And there is a clear pattern that you can see on our Open Energy Monitor that our calculation is getting closer and closer and closer and closer to the actual heat loss, sometimes to our detriment, but that's a different story. So if you want to create a feedback loop where you're not doing calculations just for the sake of calculations, having that feedback loop with Open Energy Monitor is absolutely invaluable.
Absolutely. There's nothing that beats learning from the real performance of buildings.
This video is a little bit different to what we've been doing on this channel, and I'm very curious to hear your feedback. Please let me know what you thought about this concept in a comment section below.
And if you're already doing heat loss, I'd love to understand more about how you're doing it currently. Tell us your current method, and also let us know any questions you have, things we can help with in further videos.
In the meantime, before we make more videos together, you can see Urban Plumbers putting all this theory into practice on our channel. So we'll leave another link for you right here.